In software engineering, we are taking chapter number 12, Design Concepts. In design, a very important aspect is refinement. Refinement is clearing, is to make things visible and to take out anything which is not required. So stepwise requirement in software design is a top-down design strategy approach, and it was first proposed by initially Nicholas Wirth. So whenever we develop an application or a software or a system, this is developed by successively, one by one, refining levels of procedural detail. That is, for example, you have a procedure. So we have talked about the procedural abstraction. How do we decompose it? How do we decompose it in stepwise function? So first we made a function. But before making this function and giving what is the, say, the input types, we need to have a class so that we can tell that whether this function is going to this class or that class. Then we will refine it as like this, what you see here. And then you will put content inside. That is, first of all, you will make a class, or you will define the encapsulation or the way where the functions will be decided. Then the second level of refinement is you will give the input type, the name, etc., return type. Then you will give the actual implementation or the way to implement. So decomposing in a way so that programming language statement can be generated. So refinement is elaboration. First we start with a statement that what will be the function. We will not tell about the internal working of the function or the structure of the information. We will then elaborate more information, giving more information at each successive refinement, that is elaboration. One more important thing here is these are two words here, abstraction and refinement. Now these two are complementary concepts to each other, because abstraction is suppressing the low level details and refinement is revealing the low level details. So it seems to be contradictory, but in fact they are complementary. So in abstraction, what do? We specify procedure and data internally, but we try to suppress the outsiders, the knowledge of low level details. We don't want to open up the details. For example, we define two components. Okay, so we will open only that thing which is required for certain requirement functionality to be achieved, not everything, right? So abstraction is higher level, then low level, then lowest level, finally giving all the information, but abstraction is keeping it away from others, and refinement is revealing the low level detail. Aspects. First of all, aspect is a representation of a cross-cutting concern. Now what is this? What do we mean when we say cross-cutting concern? So concern, aspect, thought, something which has to be pondered upon. So in requirement analysis, there are certain concerns uncovered in requirement analysis. These concerns can be what? It can be requirements, it can be use cases, it can be features of the software, it can be data structure being used, it can be quality of service issues, it can be variants, it can be intellectual property boundaries, it can be the collaboration between different interfaces or the classes, the patterns being used and the contracts. So the concerns is a big term, including all these. But some of the concerns, they span or they go entirely to the system. That is, it is not easy to compartmentalize it, to modularize it, to divide it. We discussed earlier that if the problem can be defined or can be modularized or it can be divided, we will be able to handle it properly in an efficient manner. But certain concerns, we cannot do that. because it is spanning to the entire system. It will be there always. So requirements are refined into modular design representation. So aspect is cross-cutting. As I said, I will try to give you an example of this cross-cutting concern. Just consider that we have two requirements, or you can say two subset or set of requirements, A and B. There are two requirements, A and B. Now you will see where the cross-cutting happens. And this cross-cutting will be aspect. One is A, one is B, two requirements. Okay, for example, 50 requirements are there, 4 A is there, 5 B is there. So it can be subset also. So requirement A cross-cuts requirement B. This is the implication or the representation of the cross-cutting. That is, if a software decomposition or the refinement chosen in such a way in which B requirement cannot be satisfied without taking A into account. So if you want to refine B, it will not be possible until we take A into the account. A is already there. A is spanning entire system. So let us take an example, proper example. We have discussed about the Safe Home Assured web app. That is the security system at the house, or you can say different CCTV camera, etc. So requirement A, we have already defined. Let me define it again. It is ACS DCV, that is access camera surveillance via the internet and display camera views. What does it mean? A person, wherever he is or she is, he or she may be able to access the cameras from wherever they are. This is the requirement A. So how do you refine it? When you want to refine this design, we would like to make those modules that will make the person accessing the camera from anywhere. But one thing, added thing is the person has to be registered. If I have taken the product, I'll be the registered person, you will not be. So here comes the requirement B. Requirement B is a generic security requirement required for all. That is, a registered user must be validated before or prior to using this website or web app. So a person has to be registered, then only you will be able to complete A. So B is the required fact. Then only you can talk about A, and you want to refine A. When you want to refine this design, you have to think about B also. So this requirement is applicable to all the functions that are available to any registered safe home users. So as the design is refined, we will make A as say A star. This is the, you can say the refined design. B is B star. So A star is a design representation of requirement A, B star is a design requirement representation of requirement B. So A star and B star are representation of concerns. And you see, B star is cross-cutting A. Without B, A cannot happen. You cannot refine A until B. So these are the aspects. Cross-cutting is the aspect. Aspect is representing cross-cutting concern. If you want to complete A design, you have to think about B also. So design representation B star of the requirement, that is, a registered user must be validated prior to using this website or web app, is an aspect of this safe home web app if you are going to make it or implement it. So aspect, ideally, I'm not saying it happens, but ideally as a software programmer or software person, you must know that these aspects are implemented as a separate module, as a separate component. Okay? Not always possible, but it has to be. If you are able to do it, it will be very good. Refactoring. Refactoring we have already discussed. So you have made a code, written some code or written some design, but this design or code can be simplified, can be made more efficient. So refactoring is a reorganization technique that simplifies the design or code of a component without changing its function or behavior. For example, 2 lines are there, they are not required, you can make it as 1 line. More efficient it will be. So Fowler, he defines the refactoring as refactoring is the process of changing a software system in such a way that it does not alter the external behavior of the code or the design, yet it improves the internal structure. So we are just playing with the internal code or design so that it is more efficient, more maintainable, more testable, but the output behavior remains the same. For example, here is a life of a software engineer. He is given a clean path. Now he wants to make something. He has all the tools, he has all the knowledge, but what he made? Now you need to refactor this kind of thing. Otherwise, it will be difficult for you and the next people to come. So when software is refactored, there are certain benefits. The existing design is examined for redundancy. Unused design elements can be removed. If algorithms are inefficient or they are unnecessary, they can be removed. If you have data structure which are not to be used or they are poorly constructed, you can also try to refactor that. Or any other kind of design failure that you may correct, that will give you a better, efficient, workable design. For instance, in the first design iteration, you encountered a component you made and it is not showing cohesion, it is showing low cohesion. Because you need to for the component to be cohesive. But after you consider very carefully, you decided you can make 3 more components or 2 more components out of it that will be showing or that are showing high cohesion. This is called refactoring of the design. Okay. In design, especially in the object-oriented design concept, all the object-oriented paradigms are being used. We start with class, define the objects, message passing, the abstraction, the encapsulation, inheritance, and finally the polymorphism. All these are used, all these are applied, all these are implemented. The object-oriented paradigm is widely used in modern software engineering. So these OO design concepts all are there. Design classes. So when we are actually talking about the classes to represent the real life scenarios, in the analysis model requirement engineering part, we already define a set of analysis classes. But at this period, the requirement engineering, the level of abstraction of this analysis classes is relatively or quite high. We are just saying this class we are going to make. But as we refine and define and reiterate the design model, we define a set of design classes that will refine these analysis classes, because now we are providing design detail for classes to be implemented. So there are different type of design classes, each representing a different layer of the design architecture that can be developed, that can be implemented. So these are the 5 different types you must understand. Different layers, and you may use all of these, you may have few of these. For example, this is a kind of architecture and you define layers. Now you have defined the components also, the classes also, and various other factors. But these classes, where you have to put and what content you have to give in these classes, this is what we are going to discuss here. User interface classes is all about human-computer interaction or man-machine interfacing. It defines all the abstraction necessary for you as a human to interact with the computer. And computer, why are you interacting? Because you are interacting with the software. Business domain classes. Now let me give you an idea. You are working in networking or you are making something for the networking people. Or let's say you are making something for the hydrology people or urban settlement people. So the business domain differs. You ought to have a business domain class, and this identify the attributes and the services, what we are calling the methods, required to implement some elements of the business domain. Coming to process classes. Now process classes, they implement the lower level business abstraction required for business domain classes. So process class is actually dependent on this or related to the business domain classes. Persistent class is all about database, data store, persistent data storage. So if you have database, you will put it in the persistent classes. System classes, and these system classes are overall boss. They will implement the software management and the control for functions for all others. So Arlo and Newstead, they suggested each design class have to be reviewed. And why we are reviewing? Because we want to be very sure that the design classes are well formed. So how do we see, how do we finalize that it is well formed? For that they also gave the 4 characteristics of well formed design class. The first is complete and sufficient. That is, a design class should contain all the attributes and methods which are required. You should not miss any attribute or should not miss any method. Okay. You need to be very open for all the content here. Don't miss. Primitiveness. Now method should focus on one service for the class. What does it mean? Class should not provide another way to accomplish same thing. I'll give you an example. For example, you have made a class and you had a function here, add. You created a function sum, and both are doing the same thing in the same class. This is the thing which I am trying to tell you. High cohesion, low coupling. Okay. Now high cohesion coupling means if you have a class 1, says we have 2 classes. Now this class, all the methods and the attributes, they should work for the same goal. They should have single-mindedness. That means they need to have high cohesion. When you have different classes or the modules or the components, the interaction between them should be as minimum as possible. The design classes collaboration should be kept to an acceptable minimum level. We cannot be having zero coupling, but as least as possible what we can have. High cohesion, low coupling is the design, underlying aspect. Law of Demeter is also there. So this suggests methods should only send messages to methods in neighboring classes. What does it mean? For example, certain classes, they work together to achieve certain requirement function or to solve some business requirement. Now these 2 classes, the methods of the functions should only pass message to these classes only, not to others which are not fulfilling that criteria. This is called the law of Demeter, right? So high cohesion, low coupling, complete and sufficient, primitiveness, these are the 4 characteristics of a well-formed design class. Dependency inversion. The structure of previous, or you can say older software architectures, they were hierarchical. That is, there will be top control component, and they will they will be dependent on, or they want these low level worker components to perform various tasks. And these are very cohesive. It is an example of great cohesion. Just consider a simple program. We have 3 components. Okay. For example, reading the keyboard strokes and printing it to the printer. So a control module, say C, is there, and it is coordinating with 2 other module. One is, say, R, which is for the keystroke, you can call it as a keystroke reader module. Then you have W, which is a module that will actually write to the printer. Now design is quite coupled, very much coupling is there, because C is totally highly dependent on this R and W. This we don't want. This is not a good design. So in order to remove the level of dependence, the worker module, the low level modules R and W should be invoked, should be called from the control module, say for example S, using abstractions. We'll talk about abstract classes here, but the main idea is the coupling should be removed. How to remove this? Because they are highly dependent, and this dependency has to be as least as possible. Let me tell you about the abstract class. This is actually a template definition of methods and variable of a class that contains one or more abstracted methods. When you declare a class as abstract, what does it mean? You will not be able to make the object, so it cannot be directly instantiated, which means that an object cannot be created from the abstract class. For example, you are making, say, a circle and a rectangle. You can make a shape and then you can give individual definition to circle and rectangle. So they will be an independent without depending on the shape. So in object-oriented software engineering, abstractions are implemented as abstract classes. For example, we talked about R. Let us say that we have implemented it as R star, W as W star. We can have a copy class, say C. Now this C, which is a copy class, will invoke these abstract classes R star and W star. And the abstract class points to the appropriate worker class. It is the abstract class which will invoke. So the R star class might point to, say, read operation within a keyboard class. In other, it can call the read operation, say, within a different class, which is the sensor class. So dependency inversion principle is all about high level modules should not depend directly upon the low level modules. Both high level, low level modules depend on only abstractions. Abstractions should not depend on the underlying details. This was already seen. And details should depend on abstraction. Detail, more abstraction, more detail. This is the dependency inversion principle. Design for test. So Rebecca wrote, the people who are advocates of test-driven development, they will, before they will write the code, they will write the test cases. And this is called the Tom Peters credo. And what they said, that test fast, first do the testing, fail the software first, and then adjust the software first and fast. Testing guides their design because they implement in short rapid fire. That is, first write the code, fail the test, write just enough to pass this, and then pass the test. These are the cycles they will make. Especially in the agile, this is done. Now, I'll talk about seams. You might have heard about stubs, etc. In software, the testing part, we will talk about that. But for right now, seams are the places in your code where you can plug in different functionality. So seams, these are the technique to help us test hard to test code, those tests which cannot be easily tested. So they allow us to replace production functionality with different functionality while testing. So we typically do this by replacing the real dependency with the test double, also called as a mock. We do this because the real dependency is something we cannot directly control from the test code. For example, we have a database or some network communication or some include file, and we are not able to actually have it. We will use seams. So if this is the example also I showed. So if design comes first, design and code must be developed with seams. Location in the detailed design where we can insert test code that probes, that find out the state of your running software. We also call these seams as test hooks. This must be designed at the component level. So, Brock, he stated, in short, we need to provide appropriate test affordances, factoring your design in a way that lets test code interrogate and control the running system. It's all about design to test. Make the design so that it is testable. Okay, this is all about this part, but we'll be taking one more part, very short part. Thank you so much.